This is Math 5700 lecture number 46. We'll be covering 8.3 today. This is our next to last lecture on new material. So today I'm going to cover something called the Central Limit Theorem, which is probably one of the most important theorems in classical probability theory. So 8.3, the central limit theorem. I'm going to formulate it in two ways. The book only formulates it really in one way. So the setup for the central limit theorem is you have an infinite sequence x1 through xn all the way, infinitely many IID random variables. Remember that IID means independent, pairwise independent, independent random variables, and they are identically distributed. So that means they have the same, in particular, the same expected value. Let's say the expected value is called mu, and the same variance. Okay. So what I want to do is consider the sum. Let's call the sum x1 plus x2 all the way to xn. Now, for example, if xi is a Bernoulli process, like you flip a coin, then n would be flipping the coin, and Sn would be the sum of the number of heads of flipping the coin n times. Now we can compute the expected value of Sn easily because it's the sum of the expected values of each of the individual things, and that would be n times mu. And we could also compute the variance of S sub n. That's easy to compute. The variance is the sum of the variances because of chapter 7. Because the variables are independent, you would get n times sigma squared. So this is from chapter 7 of the book. Okay, so this is the expected value and the variance. So what I want to do is I want to normalize this. So what I mean is I want to take Sn minus n times mu. So I subtract off the mean of Sn and divide by the standard deviation. What's the standard deviation? The standard deviation is the square root of the variance. So that would be sigma times the square root of n. Okay, so that defines a new random variable. And using the fact, I'll put it up here, that if you have a random variable of the form e8x plus b, the expected value is aex plus b, and the variance of ax plus b is a squared times the variance of x. So if you have something like that, and this is something like that, you can break up this fraction to have that form. You see that you can see that this implies that the expected value of Zn is 0 and the variance of Z sub n is 1. So we've normalized things. That's our normalization. Okay, so now, so here's the first form of the central limit theorem. Okay, it goes like this. If we look at, so we have this random variable Z sub n, we can look at its distribution, its cumulative distribution function. In other words, the probability Z sub n is less than A. Now, let's take the limit as n goes to infinity. So that means we're looking at bigger and bigger samples. then the statement is in the limit, this is exactly equal to the probability that z is less than or equal to a, where z is a standard normal. In other words, this is in other notation what I was calling phi of a, which you can look up on a standard normal distribution calculator, or if you like, using a table. So this is the distribution. So in other words, the limit of the distributions of z sub n as n goes to infinity tends to a standard normal distribution. So the upshot is the central limit theorem, CLT, is what says that for a large n, the shape of the, well, let me talk about the upshot later, okay? Because I want to get to the second formulation, which is kind of a little more familiar, okay? So now this is so what does this tell us anyway? Turns out that if so what this tells us is that we can approximate the distribution of z sub n by the standard normal distribution if n is large. So the probability that z sub n is less than or equal to a is approximately equal to the probability that z is less than or equal to a if n is large. And how large? N should be at least 30, it turns out, works in practice. Okay. So that's the statement of the result. So you have this limit is the standard, it does tend to the standard normal distribution, and for large n, it's an approximation. So let me now come to my second formulation of the CLT. Second formulation. And this is the one used by statisticians. So it goes like this. We form the sample mean, x bar, which is x1 plus x2 plus xn. So I've sampled n times. I've done my experiment n times. I sum up and divide by n. So the probability distribution of this this is a random variable, and this is called the sampling distribution for sample size n. Okay, so now we can easily compute the expected value of the sampling distribution. It's 1 over n, the sum of the expected values of the xi's, and I'm assuming that each the xi's form, again, IID, random variables. So this is going to be 1 over n. There are n of these. I goes from 1 to n, so it's n times mu, so it's mu. So the sample mean of the expected value of the sample mean is the mean of the xi's, and similarly you can compute the variance of x bar, and this is by a similar calculation. This is the variance of this sum I goes from 1 to n of xi over n, and then you can use chapter 7 material. This is going to be 1 over n squared of the sum of the variances of the xi's. There are no covariances because these are independent random variables. And this is then going to be 1 over n. There are n of these, n squared times n times sigma squared. So you're going to get sigma squared over n. That's the variance. So the standard deviation of the sample mean is equal to sigma over the square root of n. Okay, so now I'm still trying to formulate the second form of the central limit theorem. So what I'm going to do is this. Let's go back to the expression that appears in the central limit theorem. So you have the sum of everything. minus n times mu that appeared there, divided by sigma times the square root of n. And now let's multiply both top and bottom by 1 over n. What do we get? Well, if we distribute the 1 over n into the numerator, we're going to get 1 over n times the sum, which is x bar, minus n mu over n, which is mu. And then on the bottom, we get sigma times the square root of n over n, which is sigma over the square root of n. So in other words, this is the normalization of x bar we get in this way. And the central limit theorem applied to the thing I'm boxing off. So the thing I'm boxing off is also equal to the second thing I'm boxing off. So we can now reformulate in this language the central limit theorem. So the theorem says in this case, CLT theorem, the CLT second form says that if we look at the probability of x bar minus mu over sigma divided by the square root of n being less than or equal to a, that's the distribution function of this random variable, then that in the limit as n goes to infinity is equal to phi of a, the standard normal, and therefore it's we get an approximation. So in other words, the CLT says, in summary, that the shape of the sampling distribution approaches a standard normal as n gets large. And again, n should be large, should be 30 or more. So that's an amazing result. We're not going to prove it. It's actually not so easy to prove. The proof is in the book, but I'm not going to cover it. Okay, so now what I'm going to do in the remainder of today is we'll do two examples. Okay, so let me do the first example. So example 1 is, let's flip a coin 40 times, and when I say a coin, a fair coin. So n is going to be 40 here. Let x be the number of heads. So let's estimate the probability that x is as at most 17 using the central limit theorem. Okay, so now x here is a sum. I goes from 1 to 40 of x sub I, where x sub I is equal to 1 if the ith flip is heads, and 0 if the ith flip is tails. So we know that in this case that the xi's are IIDs. They're independent, identically distributed random variables. It's just a coin toss. So the mu of xi is 1/2 for all I, and sigma squared we can actually compute. We did compute it at one time for a coin toss, but let's do it again. It's the variance of xi, which is e of xi squared minus e of xi quantity squared. But e of xi squared is xi. So this is e of xi minus e of xi quantity squared, which is 1/2 minus 1/4. This is a mess. Let me do this again, which is a quarter. So that's the variance. So therefore, sigma in this case is going to be the square root of 1/4 or a half. Okay, so we know now the variance and mean of a coin toss. Big deal. Okay, so now I'm trying to estimate the probability that x is at most 17 using the central limit theorem. N here is 40, which is large enough. It's at 40 is bigger than 30. So we're now in a situation to solve the problem. The probability that x is less than or equal to 17, we have to now normalize. So that means we have to take the probability that we have to take x, subtract off n times the mean, which is a half, over 1/2 the square root of 40. Sigma squared of n, and then we have to do that to the right-hand side of the inequality. That's less than or equal to 17 minus 40 times a half over 1/2 the square root of 40. Okay, but now that's by the central limit theorem approximately equal to the probability that z is less than or equal to, we compute 70 minus 40 over 2 divided by 1/2 the square root of 40. And you can do that on your calculator. You get negative 949. And now that's phi of negative 0.949. And that's approximately, that's about 0.171. So about 17% of the time, you could expect to get 17 or fewer heads appearing in this. Okay, so that's problem one I wanted to do. Now I go to another problem. So example 2. Let's consider the following thing. The average school teacher's salary in the United States. I looked this up online. It's $47,750 per year with a standard deviation of $5,680. So so now we sample randomly of n equals 100 teachers in the United States. And we asked, what's the probability they earn less than $47,000? So what's the probability that they earn less than 47K? So let X be the salary, XI be the salary of the ith teacher in the sample. So what's the probability of X of the oh, so I wanna so let X bar equal the sample mean of the sample, and what's the probability that X bar is less than or equal to $47,000? That's the question. Okay, so that's what we want to solve, right? So so the sample mean X bar is the sum of the xi's. I goes from 1 to 100 divided by 100. Okay, so we're asking how to compute. We need to know what mu is and we need to know what sigma is, right? So we know that mu is this, and we know that sigma is this. Okay, so we want to compute the probability that X bar is less than or equal to 47,000, which I'm going to write as 4.7 times 10 to the 4th power in exponential notation. It'll be easier to deal with that if we do that. So I want to normalize this. This is the same as the probability that x bar minus n, which is n is 100, times 47,750 divided by sigma, which is 5680, divided by the square root of 100 is less than or equal to 4.7 times 10 to the 4th minus 47,750, which I'll write as 4.7750 times 10 to the 4th divided by 5680 divided by the square root of 100. And we have to close the parentheses. So this is the same thing. According to the central limit theorem, it's approximately the same thing as the probability that the standard normal, z, is less than or equal to, we have to compute what's on the right side here. And if you do the computation, you should get negative 1.32. So that's 4.7 times 10 to the 4th minus 4.775 times 10 to the 4th divided by 5680 divided by the square root of 100 is negative 1.32. And now this is then phi of negative 1.32, which is equal to 0.0093. So that is the answer to the problem. The answer is that the probability that the sample mean is less than 47,000, less than or equal to 47,000 is about that probability is about 0.093. Okay, so that is what I wanted to do today. We have one more lecture coming up in my next lecture, one more topic coming up in my next lecture, and that'll be it for the topics this semester. So there you go.